Good day, everyone. My name is Nicole G. Beltran, and I'm going to tackle about flow net construction. So we know from the previous reports that the voids within a soil mass allows the movement of water under the ground from the region of high hydraulic head to low hydraulic head, in which we call it seepage. In my report, we will analyze multidimensional flow in soil, and we will make use of a concept called flow net. So, a flow net is a graphical representation of flow of water through a soil mass. To understand the concept of flow net, let's start with analyzing one-dimensional flow before jumping into the multi-dimensional flow. So consider a soil sample of length L inside a glass cylinder. From the top of the cylinder is a water source flowing through the soil and an exit at the bottom. Piezometers are attached at different depths to record the head difference. The head difference is represented by H. Notice the water particle's movement. It moves vertically downward from the top, and the path taken by this water particle is represented by a line. That line is what we call the flow line or streamline. So since dili lang man isa ka water particle ang mag-flow, di ba? Daghan sila. So there will be an infinite number of flow lines, but we are not required to draw all of those lines. As you can observe in the piezometers, the same horizontal level has the same value of head. And so we can draw a line connecting all the points of equal head. And we can do the same for the different levels where the head is equal. These lines connecting the equal heads are known as equipotential lines. All the points on an equipotential line have the same energy. Both of these lines, which are the flow lines and equipotential lines, are crossing each other at right angles. Finally, we can see that these lines form a kind of net, and this net is called the flow net. Now that we understood the concept of flow net through this unidirectional representation, let us proceed to the representation with flow in more than one direction. Generally, the flow of water in soil is three-dimensional, but the analysis of such flow is too complex and difficult. So, we simplify the flow situations to two-dimensional and analyze the flow. So as you can see in the figure, we have three directions in the x direction, in the y direction, and in the z direction. But in our case, we just have to consider the x direction and the z direction. So the question is, how do we construct a flow net for a two-dimensional flow? There are actually a few methods of constructing the flow net, but for now, we will just use the graphical method as this is the most commonly used method of flow net construction because it is easy and it provides nearly accurate results. Let us understand this method by drawing a flow net for a hydraulic condition. So let's take a soil mass of some thickness and it lies upon an impermeable strata. A sheet pile is driven into the soil up to some depth. The left side of the sheet contains water of depth represented by capital D and small letter d for the other. We can see that there is an imbalance of head and the different side of the sheet pile. So the water will flow from high head to low head. But how will it flow? Since water cannot pass through this sheet pile, flow will take place through seepage via the soil below. So let us consider a water molecule enters the soil at some point on the upstream surface, goes below the tip of the driven sheet, and ends up at some point on the downstream surface. The flow path assumed by a water molecule is the flow line. Similarly, many particles will leave the upstream and reach the downstream, performing different flow lines. So note that each flow line begins from the upstream surface, which is at pressure unit weight W times capital D, and travels through the soil and constantly losing its energy and terminates at the downstream surface, which is at pressure unit weight W times small letter d. So we can pick up certain points on the different flow lines where the total energy loss is equal, or we can just say points of same energy level. When we join such points together, the line so formed is an equipotential line. Similarly, many different points of the same energy on different flow lines can be observed, and many such equipotential lines can be drawn. If we insert piezometers into the soil at different points along an equipotential line, we will notice water rises to the same elevation in all these piezometers. And thus, we constructed our flow net. So the space between two adjacent flow lines is called the flow path or flow channel. And the area enclosed between any two adjacent flow lines and adjacent equipotential lines is called flow field. So now let us proceed to the certain characteristics of the flow net to draw a meaningful graph. We need to take note of these characteristics. So first, two flow lines can never cross each other because flow in soil voids is considered laminar. Similarly, no two equipotential lines can cross each other because if they cross at any point, then the total head at that point will be two values, which is not possible. So the second characteristic of the flow net is that the flow lines and equipotential lines are orthogonal to each other, meaning they should intersect each other at right angles. And the third characteristic is the ratio of the length and width of each flow field, which is represented by A and B. So the ratio of A and B is A over B, and it should be constant. So generally, we take this ratio as unity or the value of 1 for convenience. In other words, the flow net consists of approximate squares, and they are called elementary squares. In elementary squares, the average distances between opposite sides are equal. So the base square is equal man ang ilahang sides. So that is why it is called as elementary squares. So to construct a flow net, we also need to identify the boundary conditions present for the flow. Boundary conditions are the restrictions that limit the flow in a certain space or area. A flow net is unique for a given set of boundary conditions. If the geometry of the flow space changes, the boundary conditions will be changed and hence the flow net will be changed also. So here, first boundary condition is the upstream surface from where the flow starts. And if we notice, it is the first equipotential line of our flow net because at every point on this line, the total head is the same. The second boundary condition is similar, and that is the downstream surface. It is the last equipotential line of our flow net. The third boundary is the sheet pile. Water molecule cannot cross the sheet. It flows from a point which is near to the sheet on the upstream and moves vertically downward, and after crossing the sheet pile, it vertically ascends. The sheet pile is also tracing the flow path of the molecule. So this boundary, if we name it ABC, is a flow line. So fourth boundary is the bottom-most impermeable surface. Water molecules cannot cross it. This line is also a flow line as the water will flow along the surface from one side to the other. While drawing a flow net, we also need to keep in mind that no flow line can intersect the impermeable boundary, as the impermeable boundary is itself a flow line. For the same reason, all equipotential lines must meet the impermeable boundaries at right angles, because the impermeable boundaries are flow lines, and flow lines meet equipotential lines at right angles. These equipotential lines are drawn in a way that drop of head or loss of head between two adjacent equipotential lines is constant, which means if head at the first equipotential line is 15 meters, and after the first equipotential line, the head has dropped by 2 meters, so the next drop should be also 2 meters, and so on. Also, the discharge between two adjacent flow channels is constant. So these boundary conditions are the rules that we should keep in mind so that we can construct the flow line as accurately as possible, or I mean the flow net. So now that we have constructed the flow net, its graphical properties can be used to calculate the seepage through soil. So let's say height of one flow field is A and length is B. We know from Darcy's law that discharge through this flow field can be written as this formula, where K is the permeability of the soil, A is the area of the cross-section through which the water is flowing. Area is the height of the flow field, A, and its width W, which is generally taken as 1 meter. I is the hydraulic gradient, which is head loss represented by delta H over the length of the flow field. So discharge through the flow field can be written as this formula. Delta H is the head loss or potential drop through one flow field. And let's say there are a number of such drops in a flow channel. Then potential drops can be represented as ND. The total potential drop or head loss through this whole flow channel is ND multiplied by delta H. Substitute this in the previous equation to find the discharge through one flow channel, and this formula can be achieved. Since two equipotential line is in between one potential drop and two potential drops has three equipotential lines, then the number of potential drops ND is the number of equipotential lines minus 1. So again, this is the discharge through only one flow channel. And if total number of flow channels in the flow net are represented by NF, then the total discharge can be written as NF times discharge through one flow field. So the formula becomes like this. Remember that the flow net is constructed by elementary squares, hence A over B is equal to 1. And finally, we can arrive at this formula. And take note that the ratio of NF and ND is called the shape factor. Also note that for a given set of boundary conditions, the flow net is unique. Flow net is dependent on the boundary conditions. If the boundary condition changes, the flow net will also change. So for example, this is our boundary conditions, so our flow net will also change. But for our change in soil, the flow net will not change. Instead, the permeability will the only one that will change. So if the upstream and downstream water levels are reversed, flow net will remain unchanged. Rather, only the direction of the flow will be reversed. So from here, we can now present some examples. So our first example, a weir is resting on a fine sand soil of permeability 2 × 10⁻⁵ meters per second. The water level on the upstream of Weir is 6 meters, and that on the downstream is 0.5 meters. The result of the flow net study gave NF is equal to 3 and ND is equal to 7. Determine the amount of seepage per meter through the base of the weir per day. So, how can we solve this? First, let us state our given. So we have our permeability of our soil, which is represented by K, and this is the value of our permeability, 2 times 10 raised to negative 5 meters per second. And the head difference of water flow, which is represented by H, is just the difference of the upstream and the downstream, which is the 6 minus 0.5 is 5.5 meters. So the number of flow channels, which is also represented by NF, is equal to 3. And lastly, the number of equipotential drops is equal to 7. So, di ba, this formula is already known from our previous slides. So, this formula is what we will use in this problem. So, we just have to substitute the given values that is stated here, and then we can arrive at this answer. Q equals 4.7 times 10 raised to negative 5 meter cube per second. But the unit is meter cube per second, and the required unit is meter cube per day. So we just have to convert the second into day. So to calculate per day seepage, we just have to multiply this answer into 24 times 60 times 60. So we all know that, right? We just converted the second into minute, and then minute into hours, and then hours into days. So 60 seconds, 60 minutes, and then 24 hours. So that is equivalent to meter cube per day. So we can arrive at this answer, 4.07 meter cube per day. So that is our final answer. So another example. In order to compute the seepage loss through the foundation of a coffer dam, flow nets were constructed. The result of the flow net study gave NF equals 6 and ND equals 16. The head of water loss during seepage was 19.68 feet. If the hydraulic conductivity of the soil is K equals 13.12 times 10 raised to negative 5 foot per minute, compute the seepage loss per foot length of dam per day. So this is the solution. So the equation for seepage loss is this formula again. So we just have to substitute the given values. So Q equals 13.12, which is the value for K, 13.12 times 10 raised to negative 5, multiplied by the value of H, which is 19.68, multiplied by NF over ND, which is 6 over 16. And then we can arrive at 9.683 times 10 raised to negative 4 cubic foot per minute. So, since the required answer or the required unit is cubic foot per day, and then we can just convert the minute into days. So we just have to multiply this by 24 times 60. And then we can arrive at this answer, which is 1.39 cubic feet per day per foot length of dam. So that will be our final answer. So that is all for my report, and these are the references that I've used for my report. So you can check them if you want to have a deeper understanding regarding this topic. So that would be all. Thank you.